Okay, so let me introduce the second speaker of this summer school. This is Professor Sophie Morier-Genoud, and Sophie is a professor at Paris 6 University of Pierre and Marie Curie, and the topic of the series of lectures will be arithmetic and combinatorics of Conway-Coxeter frieze patterns. So please, Sophie.
Okay, so hi everyone, and thank you for coming. I'm very happy to participate to this school, so also many thanks to the organizers. So my lecture is on arithmetic and combinatorics of Conway-Coxeter frieze patterns. And today I will just give a really introduction on the topic. And just to introduce the main characters. So for the arithmetic side, we will need the notion of continued fractions. I don't know if you are familiar with these fractions, so I will define them. Then, of course, I will give you the definition of Coxeter frieze. And for the combinatorial side, I will need the notion of triangulations of polygons. And so I will discuss this in the third part. I will use my iPad as a whiteboard. So I'm going to write, and everything can be made available later as a PDF file if you want. So let's start. So what is a continued fraction? If you pick a real number, x, of course, you know that you can insert x between two consecutive integers. So let's call them a and a plus 1. A is an integer. So you have 8x, which is a, an integer, plus something else you need to correct. The correction term is something positive. I mean, if x is not an integer, there is something positive and smaller than 1. So I will rewrite this extra term as 1 over x prime. Okay, so here I assume that x was not this integer a, and I write the correction term like this, so x prime is bigger than 1. And again, I can focus on this real number x prime. And this x prime is between two integers, a prime plus 1. So I can say that it's some integer a prime plus an extra term, which is bigger than 1, and that I can rewrite as 1 over x second double prime. And you can play this game again and again. And depending on the real number x you chose at the beginning, you can play this game for the rest of your life, because this can be infinite. So I will use the following notation. I mean, x, I will number all this integer produced in this way. So a2, a3, and dot, dot, dot. So here a1, I mean, all the a's are integers, but a1 may be negative, and the rest is positive. Okay, so if it stops, it's because your real number x was a rational number. And if x was not a rational, this will never stop. So let me mention this. So the sequence of a is finite. If and only if x is a rational. let me let few moments to think about this, and let's call this a proof, but it's gonna be kind of fast proof. Of course, it's the sequence is finite. Here, if you have something finite, then you can rewrite everything as a single fraction, numerator, denominator. So it's clear that if it's finite, it is rational. So this direction is okay. For the other way, if you have a rational number, why would you stop at some point? This is due to the Euclid algorithm. So the keyword to prove the converse is to use Euclid. What do I mean by Euclid? If you start with a rational number and you can start writing P as A1Q plus some remainder R1. R1 will be positive and smaller than Q. And then you can make the division between Q and R1 and write Q as A2 R1 plus R2. And now R2 is still positive and smaller than R1 and so on. And I guess you know this algorithm. This sequence of R is decreasing and they are natural numbers. So at some point you obtain 0, so it stops. And the AI that you have here in this division are exactly the one that you would get here. So this continued fraction is another presentation of the Euclid algorithm. So that's one thing. Another thing, one can do some other approach. Here, I started with a smaller integer and add the correction term. I can do the opposite. I can opposite approach, meaning I can choose the bigger integer and remove the extra term, okay, the extra quantity. So, and this will lead to expansion with negative sign, which so I will mention them as negative expansion. Or sometimes in the literature, it's known as Hirzebruch-Young continued fraction. So let me give you the keywords: Hirzebruch-Young continued fraction. And basically it works the same, but now you remove the extra quantity. I mean, you remove the to get what you want, and so on. So when you deal with the two expansions, this time this one will be referred as the regular expansion, and this one the negative expansion. And I will use the following notation. I will use brackets. So the sequence of A's between square bracket like this is a notation to express X as a regular expansion, as a regular continued fraction. And for the negative, I will use a double square bracket. So this. So let me give you some examples. Let's start with irrational. That's maybe the most interesting numbers, because this sequence will be infinite. As I said, for the rational, it's just Euclid algorithm. And so, okay, let me, maybe, you know, if you want to think of an irrational, one that can come into mind, maybe the golden ratio. And this one has a very simple expansion as a continued fraction. You maybe already seen that. it's just the expansion with the ones. So it's the infinite sequence of ones will lead to the golden ratio number. Another irrational that can come to your mind is the number e, the Euler number, the value of exponential at 1. And yes, this one is for the golden ratio, it's kind of easy to understand why this is that. For the Euler number, I don't know. Euler computed the expansion long time ago without computers. I don't know how exactly he did, but the result is quite amazing because there is some regularity in the sequence. So let's look. So you know that the integer part of O is 2. It's 2 dot something, and then so the expansion is 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, and so on. So there is this kind of regularity. 2, 4, 6, 8 between a couple of ones. So it's pretty nice. For the other very famous irrational number pi, here there is no regularity at all. So I'm just copying what I see on my screen. So it's 3, 7, 3 is the integer part of pi, 15, then 1, then 292, then 1 again. So it's quite amazing. It looks really like random numbers. But pi has generalized continued fraction expansion, which are very, very nice. Here, I focus on 2 types of expansion. This with plus and only ones. And here, this negative signs and only ones. But you can generalize, of course. And instead of having a +1 here, you can make also arbitrary numbers. This will give you a generalized continued fraction. And pi has really, really, really beautiful generalized continued fraction expansions. I just stole from the Wikipedia page. So just to show you some kind of amazing formula for pi, if you allow arbitrary number on the top, for pi, you will have this beautiful regularity of this odd number squared. Here you have only 2s. You can also find a formula like this, the natural number squared, and here the odd numbers. And Wikipedia is full of, not full, but you can find more. You can find more such formula for pi. So if you were already asking yourself why one should care about continued fraction, I think this is just an answer. It's just when you have something beautiful like this, you know that you have an interesting object. Okay, so let me give an interesting example for negative expansion. What happens if you look at, so I use this double square, so now I'm considering the negative expansion. And if I choose a sequence with only 2s, do you have any guess of what I would obtain? I don't know if I can monitor the chat at the same time, but let me try. I have a suggestion of golden ratio. It is not the golden ratio. Okay, I have a lot of suggestions from this. There is I will answer. I'm looking at the chat, so I will answer. Okay, there are a lot of creative. So I think I saw
a question. There is also a question.
Yeah, I saw that. So let me just finish with this expansion with only 2s. So Cameron gave the right answer. It's going to be 1. It's maybe not easy to see at the first time, but this is not an irrational number. And it's just the integer 1. I did not say, because it was not true, I did not say that we had the same statement for the negative expansion. And this is a counterexample. 1 may be represented with infinite sequence, okay? So for the uniqueness question, this gives you the uniqueness. And asking for the CI to be bigger than 2, but not infinitely many 2s, this will give also the uniqueness of the sequence CI. Okay, so this one is a little bit more involved to use. I mean, when you have to be careful in the statements because of this property. So if you want to write the similar statement, you have to say X is a rational if and only if the sequence of CIs is finite or ends with only 2s. That's the way to have a correct statement here. Okay, more examples. It's already prepared on my board. Actually, I said that irrational numbers may be more interesting, but for the rest of my of the lecture, of the course, I will usually only think of rationals and rationals greater than 1, because I want to do combinatorics. So I want positive numbers to be able to count things, and also I want finite sequence. Okay. So here for rational, the sequences are unique. The finite sequence representing a rational are unique with this condition. So if I ask this, and if I ask here, so C1 may be whatever, but after starting at 2, then the CIs are greater than 2. So for the rational, if I want a finite sequence, this condition makes the expansion unique. Not really for the rational, sorry, I have to remove what I said. There is an ambiguity at the end of the sequence for the regular expansion. Let me maybe I put a remark here. Remark. To make it unique, one can always choose the even number for the length of the sequence. So in the regular expansion, I can always assume that n is even, and this now make no ambiguity. Why do I say that? It's because if you look what happened if you have a1 over and so on, what happened at the end? You can, if an is bigger than 1, you could artificially do something like this, you know. If an is greater than 1, I can add I can change the last coefficient like this. I remove 1 and then I add +1 over 1. So I increase the sequence of A by 1. Or conversely, if the last number is a 1, I can always add it to the previous coefficients and shorten the sequence. So I will always assume that in the rational, so here I am talking about rationals greater than 1. And for the regular expansion, I always choose the one with the even number of terms. Okay, so let's maybe go over the example here. 5/2. It's pretty clear. You can do it in your head. It's 2 plus 1/2. That's what I mean by this notation. This 2 refers to these two numbers. What I was explaining just in the remark is that I could have said that it is 2 plus 1/1 plus 1/1. So I could have written that it's the expansion 2, 1, 1. But I don't want an odd number of sequence of terms in the sequence. And for the negative expansion, also you can compute in your head that 5/2 is 3 minus 1/2. And so these 3 and 2 refers to the coefficient here. Okay, so for 10/3, also maybe this one is quite fast to compute. But then the more complicated is the fraction, the rational number, and the more computation you need to make. Okay, so the question I want, there is a very natural question, so I want to address for today. So that's the question 1. Given x, a rational number with regular continued fraction like this, and with negative continued fraction like this. What is the relationship between the coefficients a's and c's? That's a very natural question. What is the relationship between these two sequence of coefficients? I'm not going to answer right now. I will postpone the answer later. If you look at the example, it's not clear at all. First of all, it's not clear even the relationship between m, between the length here, and between k. Sometimes you have the same number of terms. Sometimes the negative one is longer, sometimes it's shorter, sometimes it's much more longer. So even the relation between n and k is not clear. And the only thing that is clear is the relation between the first coefficients, because this one is the integer part, and this one is the integer part plus 1. So C1 is always A1 plus 1. Okay, that's clear. But then for the rest, no idea of, at the first sight, no idea of what is going on. Okay, so that's just a brief introduction to continued fractions. I will go back later on the question. And now I want to talk on frieze. Are there any questions in the chat? Okay. So here, I already prepared an example, but now we need the definition. First of all, let me tell you that this is due to a mathematician Coxeter in a work in the 70s. And we have an example already written on the board, and let's try to guess the definition from the example. So what can we say? What is a frieze? As you can see, it's an array of numbers. What can we say? The array seems to be infinite because there are these dots. The top row is a row of ones. The last row is a row of ones. So this is part of the definition. First and last rows on ones. And then you have this number inside the array, and you may wonder what's going on. And so there is a rule behind these numbers. There is something that they need to satisfy. And I don't know if it's easy to guess, so let me just give you the rule. So the rule is that when you have four numbers like this, A, B, C, D, in the array, what you want is that you want that A, D minus B, C equals 1. Okay, so product of horizontal is one more than the product of the vertical. So it's satisfied everywhere. I have hidden a value here with a question mark so that everybody get familiar with the rule. So now everybody should think what is behind this question mark. And maybe I can write an answer in the chat, but I think it's easy, but just to practice the rule. Okay, we have a good answer in the chat. So indeed, the hidden value was the number 5. So let me change this to a 5. But of course, the first diamond that you can choose, let's say this one, for instance, will give you that you have to have 5 here. You want this product to be one more than this one. So we had this value, so it was 14. So you need a 5 here. But to have a frieze, the rule have to be satisfied everywhere. So don't forget to check that. We also need to check here that 21 is in 20, 10 and 9, and also here. Okay. So this is so this will be the main object for the next lectures. So I'm not going to reveal everything today about them. I just want to give one property, which is the following. Let me call this theorem. It's in the work of Coxeter. The first amazing thing is that the frieze are periodic. And I can predict the period. So let me introduce some data here. I need to know how many rows are between these two rows of ones. And I will call this the width. So on the example, it's an example of width 4. I don't count the rows of 1. So 1, 2, 3, 4. So it's a frieze of width 4. And I can predict the period. The period will be 7, width plus 3. And indeed, if you look at what happened here, here I have a 4. And if I count a 1, 2, 3, 4, 5, 6, 7, there is this 4 that repeats. The 3 repeats here. The 5 repeats here. The 3 repeats here. So if you, for example, if I extract these values here, if I take these 4 values, you may understand that it's enough to know these 4 values to know the rest of the frieze, because there is this rule. Because of this rule, you will be able to fill the rest of the frieze. And what happened is that at some point, again, you will recover the same zigzag of values here. So that means that everything that you have computed here will repeat here, because you will use the same rule. So the entire frieze is periodic. So you don't need to show the entire frieze. You just need to focus on a small part. And it's actually better than that, because there is what we call the glide symmetry. the glide symmetry is that here this, if I extract this triangle, what you can see is that the values that I have here, 1, 4, 3, 2, 1, 1, they repeat here, but after a flip, 1, 4, 3, 2, 1, 1. Because of the symmetry of the rule, this means that everything that you have in one triangle will repeat in the other triangle after a flip. Okay, so that's kind of two magic properties of frieze. So let me finish the statement. Frieze are periodic, and if it's of width W, then W plus 3 is a period. I told it, but I did not write. It's not necessarily the shortest period, but so, or let's say that the period divides W plus 3. Generically, it is the period, the shortest period, but in some examples, you can find a shortest period, a shorter period. This is and the second statement that I have illustrated with these blue lines is that it's invariant under glide symmetry. So in the next lecture, I will give you more properties. I have prepared also this problem sheet. So in the first exercise in the sheet, it's just to practice the rule. So I would recommend you to have a look at these problems. It may look kind of long because writing the frieze takes place, but I think you can do it very fast. So if you do it tonight, maybe it will help for tomorrow lecture. And let's say the first, no, the exercises 1, 2, 3, and 4 maybe a good practice for tomorrow. Okay, and of course you may also wonder, why is this interesting? Why frieze and why do we care? So far it just looked like some entertainment. If you have a long journey in the train, you just fill your frieze with numbers, like a Sudoku. You have numbers, you have rule, and you do it. But it is actually really, really deep. I mean, the frieze, this Coxeter frieze are connected to very, very fundamental mathematics in geometry, in number theory, and also in modern mathematics. There is a recent theory of cluster algebras. I would say also a few words about them, and frieze are connected to this theory. So more to come tomorrow. For today, I just want to address the following questions. So that's the question 2. How do we get frieze with positive integers? I gave you an example. So how to get a frieze containing only positive integers. If I give the frieze, of course, you can check that it's a frieze. It's just the rule. It's periodic, so you don't have infinitely many verification to do. It's just kind of fast. But the magic thing that is behind this frieze is that it's only with positive integers. And if you think a little bit about it, if you want, I said it's like a Sudoku. So you need initial value somewhere, and then you fill. But if you imagine that you know these 3 numbers, A, B, D, if you know A, B, D, let me change the color to, if you want to get C, what do you need? You need to do AD minus 1 and then to divide by B. So the operations you make involve a division. So you can put integer at some place, but the rule will involve division. So if you want integers, you cannot choose random value. Same with on the other way. If you know ABC, if you want to compute D, you need to do, what do you need to do? 1 plus BC over A. So this formula has an advantage is that there is no negative sign. So at least if things are positive, it remains positive. And with this formula, it's not clear what could happen because there is a negative sign. So maybe you will get to some negative value. So it's really not really not obvious how to get a positive integer inside the frieze. I will answer later. And now I will go to the third part of this first lecture, which is the introduction to triangulations of polygons. So sometimes I will say n-gons to refer as to the number of vertices or the number of sides of the polygons. And here we have 7 gons. 1, 2, 3, 4, 5, 6, 7. Yes, 1, 2, 3, 4, 5, 6, 7. So there are 7 gons that we can also call heptagons. And a triangulation of a polygon is to draw diagonals. So what is a diagonal? A diagonal is a segment joining 2 vertices, which are not a side, which is not a side. Okay, so the diagonal join the vertices that are not consecutive. So, for example, here I drew 4 diagonals, and to get a triangulation, I need the diagonals to not cross, to not intersect inside the polygon. So the polygon is supposed to be convex. I choose a convex polygon, and a triangulation is to draw diagonals so that they don't cross, and you draw the maximum as you can, and you will get a division of your polygons into triangles. So of course there is no, it's not unique. You can change the picture, for example. So here are 2 triangulations of an heptagon. And this is a very classical object in combinatorics and enumerative combinatorics. I don't know how much I would have time to tell you about triangulations. Of course, I cannot resist to first think about the number of triangulation. If you fix n, if you fix a polygon n-gon, and if you want to ask how many different triangulation I can get, does anyone know the answer? It's a famous number in combinatorics. Yes, yeah, Catalan. So the keyword is Catalan if you want to count how many triangulation you have. And this makes a link to the previous lecture, because this is also the way you can count a standard tableau with 2 columns. So, I mean, it's a famous sequence, the Catalan numbers, that appear in many different type of problems. Okay, so I hope the definition of triangulation is clear. What happens when you have a triangulation is that you will always have what I want to call a ear, meaning that there are triangles that are kind of exterior. I know this triangle, if I remove this triangle, I still have a triangulation of some smaller polygon. It's not the case if I remove this, disconnect the picture, okay? So in a triangulation, you always have 2 triangles on the border somehow, but you may have more. Here I have 3 exterior triangles, okay? So I want to focus for a moment on these triangulations with only 2 exterior triangles. exactly two exterior triangles. In these triangulations, I have the following property. If I draw the diagonals that join these external vertices, this diagonal will cross all the other one in the triangulation. So I fix a triangulation in which I only have, I exactly have two exterior triangles. I can join these two exterior triangles by a line, and this line cross all the other triangles and cross all the other diagonals already in the triangulation. It is not the case here. I cannot find a line that cross all the triangles if I have more than two exterior triangles. So for these triangulations, I will record them in kind of with two different data. Okay, so let me try to explain this. It's going to be a rough picture of a triangulation with this property. What happens? This line, this red line, organize the triangulation as follows. There are triangles that have the base above the line, and then there are triangles that have the base under the line, the red line. So here it's a kind of small picture, so you cannot see, but basically what you have. Sorry, there is a question in the chat. The number of triangles. Yeah. So for the question, is the number of triangles of a triangulation depending only on n? Yes. You have n minus 2 triangles always in a triangulation, and you have n minus 3 diagonals. It's a fixed. There are fixed number. And then there is another question: does the converse hold if we can join two? Yes, the converse hold. If you can find a diagonal that crosses every other diagonals of the triangulation, then it's because it has only two exterior triangles. There are many properties that are kind of very intuitive, and if you want to write down, it's sometimes always some induction, but it's also easy to write a real proof. Okay, so let me finish with what I'm seeing. So these triangulations I can roughly represent like this. So you have a sequence of triangles that have the base under the red line. Then you have triangles with their base above the line, then under, and so on. And at some point it ends. Okay, so I can, so let me put the vertices. So here are the vertices. So now the polygon doesn't look convex, but it's because it's easier to do like this. So what I'm saying here is that it's a collection. So for, oops, you have, let's say, A1 triangles here. Then, so you have A1 triangle with the base down. Then here you have A2 triangles with the base up. And then A3 triangles with the base down, and so on and so on, up to some points. Let's say here you have A2m minus 1 triangles. And here you count A2m triangles. So if you know this sequence of A's, you know the triangulation. But there is another interesting statistic that you can do, is that you can also count at each vertex how many triangles are incident to the vertex. So let's me introduce this CI. CI is the count, the number of triangles at vertex I. Okay, so let's do it on the example that we have to make it clear. So for instance, here. Here I had only one triangle. It's because it was an exterior triangle. Here I count two triangles incident to this vertex. Here I count, oops, sorry, what I'm doing. I count one triangle. I count two triangles. I count two here. Here I count 1, 2, 3. Here I count 1. Here I count 1, 2. Here I count 1, 2, 3, 4. So this is the sequence of CI for the triangulated heptagon that is here. Okay, so I can put this number, attach the number at each vertex. So for example, here it was C1, that's vertex 1. So I count C1, I count C2, I count C3, I count C4, and so on. I count K plus 1, which is 1, Ck plus 2, so on. And then the last vertex, Cn, is also 1. These ones are because of these two exterior triangles. Sorry, yes, it's 1, 2. And the sequence of A's determines the triangulation, and the sequence of C's also determines the triangulation. It's two alternative ways to record the triangulation we are talking about. So let me note this here. So the sequence A1, A2, A2M determines the triangulation. And the sequence C1, C2, and so on also determines. You need only one of these data. Theorem. So with this data, if I am given a triangulation like this, I look at this sequence of A's and I compute the rational number A1, A2, A2M using this continued fraction expansion, the regular. It's the same as the rational number that I will compute using the C's up to Ck and the negative expansion. So this is the answer of question 1. The question 1 was a relationship between the A's and C's in the continued fraction expansions. And this is somehow the combinatorial interpretation of the relationship. Second point, so be careful here, I stop at K. So this is the last one I need to compute the rational. But if I go all the way, if I consider the entire sequence C1, C2 up to Cn, this will give me the first row of a Coxeter frieze. This determines a frieze of width n-3 with positive integers, containing only positive integers. Okay, so I hope what I'm writing is clear. This, I know that the frieze is periodic. So if I take this sequence of C's that I obtain from a triangulation, I put it periodically in the first row of a frieze, then I compute with the rule of the frieze what I would get. I would get n-3 row with numbers, and the next one would be a row of 1. So I will start with a row of 1, start with the row of the C's, compute, then at some point I will get back to a row of 1. So it's a kind of magic. And maybe have a look at the time. So 10 minutes. So just 2 comments. Are there any questions? Let me just, so these are the answers of the 2 questions. I hope it's clear. So remark on one is that now if you, because you have this the picture behind this formula, you can write down things which is called the Hirzebruch formula. So that's the formula for the conversion. If you have this A1, A2, A2M, it's a rational number, and the continued, the negative expansion is the following. So if you want the first coefficient, sorry, I'm looking at the negative. So I want to convert the regular continued fraction expansion into the negative expansion. So I use the picture. I know that this number counts how many triangles are incident at vertex 1. So I have A1 triangles with the base down, plus 1 triangle with the base up. So this is A1 plus 1. We already knew that, but we checked on the picture. Then I want to, the next coefficient will tell me how many triangles are incident to the second vertex here. And it's only 2 because they have the base up. And the next one is also 2. So I have a long sequence of 2. I have a sequence of 2. But how long is this sequence? I need to know how many vertices I have here. I know that I have A2 triangles. That means that here I have A2 minus 1 vertex. So here I have A2 minus 1 vertices with 2 incident triangles. And then again, I need to count how many triangles I have here. So I have A3 plus 2 and so on. So A3 plus, sorry, up, A3 plus 2. And then I have again a sequence of 2 and so on. So I can really make a conversion very efficiently from the picture. So that's the first remark. The remark on the second statement here is that it works with all triangulations, not only with these particular ones. So it works with any kind of triangulations. Meaning, if I consider this triangulation, it doesn't have this property, but the sequence that I will get here is 1, 2, 3, 1, 3, 1, 4. And this sequence, write it in the first row of a frieze, compute the frieze. You will get only positive integers, and you will get a frieze of width 4 because it's a heptagon. Okay, so and all friezes arise this way. So this is the Conway-Coxeter theorem. And actually, when I say Conway-Coxeter theorem, I mean, when I say Conway-Coxeter frieze, it means frieze with positive integers because of this result. So, and this will be one of our goals. So it's now the end of the lecture. So let me tell you the goal for the next lecture is to understand this. Okay, we want to understand that this combinatorics give a frieze. We want to understand that this is true. So I will tell you more about this next week. No, tomorrow. Are there any questions in the chat? Yes. It's the same for the Hirzebruch formula. You don't really need to have a even number of terms, but I mean, what happened is the ambiguity that you have on the fraction, you also have it here on the triangulation, because I could have considered that this triangle is has the base. Let me change the color. I could have, I did not change the color. The way I see the last triangle, I want to see it as with the base up, but I could have written with the base down, and it doesn't really change the picture. I mean, the counting. It's just so for the, if you want to write the Hirzebruch formula, the best is to make sure that you have an even number of term in the expansion. Otherwise, at the end, it's just some little corrections that you have to make. I don't know if okay, it's understood. Okay, so maybe I just was not sure I had time, but just we can practice an example. Sorry about this. Earlier in the course, I gave you that this fraction is 2, 1, 2, 5. And so if you want to convert to the negative expansion, just draw the picture. So you draw 2 triangles, 1, 2, and 5, 1, 2, 3, 4, 5. And then to get the negative expansion, it's quite fast. You count. So I count 3, so in red, to be consistent. So here you count 3, here you count 1, 2, 3, 4, 2, 2, 2, 2. So that's the answer. And it's very fast to convert the regular to the negative. It was announced in the example. And if you want to practice the theorem, I say that this is the frieze of, this is the first row of a frieze. So take these numbers, 1, 2, 2, 3, 1, 2, 4. I don't know, maybe that's the one. 1, 2, 2, 3, 1, 2, 4. It was the one coming from this frieze. So let's practice on this one. So you take 1, 2, 3, 1, 3, 1, 4. 1, 2, 3, 1, 3, 1, 4. You draw this, you put this in the first row of a frieze, and then you compute, and then you compute, and you will check that at the end, 3, 1, 5, 3, no, why did I write 1 here? And so on, and you will see that it will end with a row of 1, 4, 3, 1, 5, 2, and here it's already. So write this cyclically in the frieze, 1, 2, 3, 1, 3, so 1. So here 4. You can, you can practice with the example of your choice. Choose a triangulation, compute the fraction, compute the frieze. It's going to be a way to practice with all the material of today. So sorry, I don't want to be over time. So thank you for your attention.